Welcome to the Grasp on Robotics seminar. Quick logistics note, this is being recorded but not Zoomed, and kind of all of the seminars go on the YouTube and the website. It's my delight to be the faculty host and to welcome Kris to Penn and to Grasp. Kris will be wearing his UIUC hat today and not his new Samsung hat. He's done foundational work in planning and control and perception applied to rock climbing robots and steerable needles and warehouse logistics and granular media and fruit picking. And I guess you're now just calling it stuff to kind of encapsulate everything. To me, Kris is someone who has a kind of deep love for getting robots to actually work and thinking about things on kind of a systems level. Going from very theoretical groundings up to very practical things like clamped. And if you have not used his In Progress Robotic Systems textbook on his website, I would recommend it as a reference. Kris is someone who seems impervious to hype, which is personally entertaining to me in this moment, because my favorite paper of all time is a humanoids paper by Kris from like your PhD work.
Oh, okay. Thank you.
And I think maybe part of being kind of grounded in systems work and being kind of impervious to hype is that I do think of Kris as someone who really values and pushes for academic argument and debate, and that your ideas should stand up to a pummeling and rigor. So we normally say, hold your questions to the end. I will say, I think the kindest thing and most Kris thing we can do is to kind of besiege him throughout. I only ask that you kind of give me time to get the mic to you so everyone can hear. But Kris, super happy to have you today.
Thank you so much for inviting me, Rachel. And that was a fantastic introduction. And yes, that would be actually very fun if you could please pummel me with questions. That's actually one of the best introductions that I've gotten for one of these kinds of talks. Excellent. So yes, so what I've been thinking about for all this kind of like systems work is, I always try to think about what is it that robots need, and that the current tools and technologies that we're using to build systems is not giving us. So sometimes that's new algorithms, sometimes that's new theory, and sometimes it's just pure kind of elbow grease and grunt work to try to get things up and running. But today I want to talk to you about something I've been excited about and interested in for the last few years, which is about how to build models of real worlds, complex worlds. And so I think we need to start thinking about the worlds as a bunch of stuff rather than really prescribing what's exactly in it. And I will say that I'm from University of Illinois, but I'm also on leave of absence at Samsung Research America. And as Rachel said, none of the opinions or comments or positions in this talk are from Samsung. So I need to get approvals for those types of talks. But so what I've been thinking is that, I come from planning, and planning is really in the center of the whole robotics kind of behavior ecosystem. Planning needs some kind of input from perception to model worlds and then make decisions. And nothing's been really satisfactory in terms of planning for the complex environments that I really want robots to be able to work in. So we have kind of two primary methodologies for building robots nowadays. So one is to think about the world as a bunch of rigid objects or articulated objects. And the other one is to start looking at end-to-end policy learning. And these both have their strengths, but they also have some key weaknesses. So rigid object worlds are very nice for precise manipulation of these rigid objects. You can explain exactly what your robot is perceiving and reasoning about. You can do, for example, mapping of objects. You can simulate them. You can plan with them. And they're also very precise when the perception is working well. But they're pretty, as rigid says, they're not very flexible. You can't deal with small amounts of deformation, such as the cushions in this room, or even just the flexing of a box. It's hard, although Michael Posa here is doing a great job of doing various forms of physics estimation for these types of scenarios, but it's really not that straightforward to estimate the properties of these objects as you're interacting with them, especially things like friction. And they're also very sensitive to your perception inputs. Now, on the other hand, policies they're having a really great time right now. They're actually really, really easy to spin up. You don't have to have a very complex system to be able to do reasoning and planning and so on. There's lots of different boxes of algorithms that rigid object worlds typically need to have. And instead, you just have camera images going into some kind of neural network, delivering some kind of outputs. So, and you can also quickly bootstrap these kinds of models using imitation learning. You can evaluate them very quickly. You don't have to wait for a planner to complete. And you can also do a lot of task level scaling to different kinds of tasks with the same kind of large neural network. But they have a lot of weaknesses in that they're not very explainable. They don't have great long-term memory. You can't really customize them after the training is done. And then they're also very sensitive to the distributions in which they're trained in. So I think we need something different. And I like to kind of think about my dogs whenever I watch them do something. This is not my dog, but it's my dogs do a similar kind of thing. So this is a little Chihuahua. It's sitting on this couch, and then somebody tosses this blanket, and it recognizes that a blanket is a nice warm place to sleep. And it tries to like poke around in here. It's trying to like understand what's going on with this thing, what its layout is. And then eventually it's going to find some way to kind of scurry underneath the cover and get itself into a nice warm spot. So all of this is being done online, right? It's never seen this blanket before, or maybe it has, but I can just toss a blanket to my dogs and they'll want to kind of bury underneath it. But at least in this configuration, this particular position on the sofa with the other dog kind of jumping into the mix, it's all being able to figure out this kind of complex situation just on its own with just online data only. So I think we need something new. And I think what we've done, so we need something new. And there's a lot of applications in robotics. We're not just building dogs that want to get warm, but we want to have agricultural robots doing various forms of agricultural tasks. We want to have robots in the home that deal with our kind of soft environments, working with humans in medical applications, also going outdoors, doing scientific exploration, off-road navigation, construction and other kinds of interactions with terrain. All of these require us to think about the world as a bunch of unstructured kind of material, or the objects that we're working with as unstructured material. So this is what I call interacting with stuff. So if we were to think about what we want from cognitive representations of worlds, neither scene graphs nor pixels suffice. I think we need to have a few kinds of desiderata. So I've been kind of using these as kind of a structure for kind of the research direction that I've been pursuing in the last several years. One is that these have to be very, very adaptive. So the models themselves need to adapt to observed behavior. And we need to be able to learn physics from interaction. We need to be able to account for deformation in the world. And it has to be deformation across the full 3D space. And so this is what I call stuff. We need to be able to integrate multiple modalities: vision, touch, audio, smell, I don't know, maybe. And we also have to deal with the heterogeneity of the world, right? We can't just kind of segment things into just objects and assume those objects all behave the same. The internal parts of an object all behave somewhat differently. The cap of this bottle is different from this area. The cushion that you're sitting on is different from the kind of back of the chair. And we also need to be able to think about kind of big data. We do need to think about big data. How do we get priors of the world so that we can make more effective use of the kind of information that we get online? Something's a little bit off here with the animation. We also need to be able to map the worlds throughout a lifetime of a robot. This shouldn't just be a single scene, but it should be building up this world as we go. We need to be also able to reason about occlusions and uncertainty in these scenes, and we need to be able to apply them to diverse tasks. And finally, we need to be able to think about the explainability of these kinds of representations and transferability. We need to be able to build databases of worlds. We need to be able to have I/O to be able to visualize and transmit them and inspect them. So, we're making some progress in these different categories, but we're not quite there yet. I'll be talking about some projects that we've been working on recently that kind of go through and check some of the boxes, but not all of them are completely checked yet. And I'll also talk about some of the future of how I think we can go about checking off all these boxes. So all these have been published in the last couple of years. So just an outline of this talk. I'll first start talking about the adaptation problem, so why it's important and also why it's hard. Then I'll talk about some of these representations for treating the world as stuff, and then I'll conclude with some of our future directions and also hot takes, which I think students tend to like. And I'll give some long views about cognition. So let's first start talking about adaptation. Adaptation is the key to this idea of treating the world as a bunch of stuff. So let me show you a video here. You may have seen this. This came out last month. This is from Skilled AI. They have this quadruped. They sawed off the legs, and it's adapting to that kind of new body that it's in. So it's got some kind of locomotion controller. It adapted to that kind of damage. You can also adapt the same kind of model to multiple types of robots. Let me just kind of zoom ahead a little bit. Let's see here. They're basically training this quadruped to kind of figure out from its starting state that it's kind of on a more like a biped, and so it ends up using the back legs to do locomotion rather than its quadrupedal locomotion. And here they also add some stuff onto the end of it, and let's see, and it still walks. So that's really cool. If you turn the sound on, it's got this nice guitar riff kind of soundtrack, and it gets you really jazzed about the future of locomotion. But and this is a very recent instance of an adaptation technique that's pretty cool. It's called in-context adaptation. I'll talk about it in just a little bit. But I've been interested in this adaptation problem for a while. It's by no means a new problem. So I kind of got started looking into adaptation when trying to have robots interact with humans. So we created the first auscultation automation robot. Auscultation is the process of listening to heart and lung sounds with a stethoscope. And here we have kind of an initial scan of the person. We identify some anatomical regions, but if you're a doctor, you realize that if you listen to a heart and lung sound in certain locations, you might be listening through a rib or some kind of other kind of tissue obstructing that sound. And so you have to start moving around that stethoscope to get a high quality heart or lung sound. You also might not know the exact anatomical location, so you have to adapt that kind of location as you go. And so our robot does exactly that using a technique called Bayesian optimization. And so it adapts its location based off of the information that it gets online. But this is a very simple form of adaptation, and I just want to kind of go through and talk about some of the details of the adaptation process just to get us kind of in the mood for the math that you need to kind of understand to kind of understand the process of the techniques for doing adaptation, the mechanisms for this and why it's hard. So the problem of adaptation is that we've got some kind of learning problem at test time. And it depends on some sort of unknown parameter that's kind of common to this kind of environment, but we don't observe it directly. And so this latent parameter theta could be anything. It could be the kind of material parameters of an object that you're manipulating. It could be some kind of aspect of the reward function. It could be some kind of, let's say, the body that you're in, for example, in that skilled video. And so this parameter theta is unknown, but your pre-training for your model can see lots of different forms of kind of sub-data sets. So for different values of this theta, you can get data sets of your inputs and outputs. And here we're talking about supervised learning. You could also kind of recast this in reinforcement learning as well. But you have these paired examples, xi, yi, but they are related just for that specific value of that latent parameter in that data set. Most of the time, you don't observe that parameter in your pre-training set, but sometimes you do. And the real issue here is that we need to take what's called a support set, right? We don't know what this theta value is, but we want to be able to take some data that we get online, hopefully a very small amount of data, and then be accurate at our predictions in this environment in which theta is active. This particular value of theta is active. So typically this is also done kind of in a kind of online kind of recursive fashion. So we make some decisions based off of our predictions. We then make some observations. We add that example to the support set once we've observed the outcome. And now we repeat. So our model actually adapts as we go to the data as we add to the support set. There's lots of different mechanisms for doing this. The most kind of standard method to do this is some kind of fine tuning. So if you're doing, let's say just online RL, you're doing fine tuning. There's other refinements of this approach like mammal model agnostic meta learning. Basically, you're just maintaining a model and you're taking gradient steps to try to reduce some sort of loss. Now, the problem with this is that it works actually quite badly in the few shot regime, depending on how you've tuned your parameters for learning. It also risks a problem called catastrophic forgetting, in that if you get enough data, then you end up losing the kind of pre-training that you used to have. Yes?
What's the advantage of looking at this problem with the robot and sequentially scanning versus X-ray tomography?
X-ray tomography, you mean, what's that?
Mentioned the previous stuff.
The previous step.
The medical
Medical application. So listening to heart and lung sounds is a kind of standard diagnostic that you get from any kind of typical physical checkup. And so it's something that doctors don't like to do. They don't have a lot of time to really do a thorough kind of scan. And so the idea is to take a robot that is kind of doing the basic medical tasks, getting basic medical signs, and reducing the demands on doctors. Yes, there are certain things, though, from heart and lung sounds. For example, if you're trying to diagnose pneumonia or some kind of an infection in the lung, you can hear various kind of aspects of the lung sound. And I'm not a doctor. I don't know exactly the specific kinds of diagnostic types of crackling or wheezing that you can hear, but you can get a lot of information from the audio that is harder to get than compared to ultrasound. Yep, thanks. Okay. Okay, so let's see. Another approach to this is trying to actually estimate this latent parameter. And this approach, if you were to learn a conditioned model that conditions your prediction on the latent vector, you can try to estimate then during runtime based off of your support set. And this can be of a form of an optimization. I'll show you one way in which we do this in just a second. But basically, you can do an optimization to match your observed data to your model to your observed data. Another refinement of this approach is to, rather than actually explicitly optimize this parameter estimator, to just learn the parameter estimator. There's this technique called a rapid motor adaptation from 2021 that does exactly that. So it's not a perfect optimization, but it does approximate it using similar model. Now, another refinement of this approach is Bayesian meta-learning. So one of the problems with learned parameter estimation is that you have to do a very careful job of regularization in the few shot regime, especially in the zero shot data. So you need it and kind of screw everything up with your kind of support set. So here you have a probabilistic model, and then you actually average over the parameter values that might exist. And I'll show you how this works in a particular case with this kind of stiffness estimation problem that we'll see in a second. We've also worked a bit with Gaussian processes, which allows you to do adaptation by assuming a Gaussian distribution over functions. This also has a nice property of being able to give you distributions of your output. So you don't just have a single estimate, but you also have a distribution estimate. And one of the challenges with Gaussian processes is this idea of calibrating the kernel. Now, if you can calibrate that kernel well, as I'll show in a future slide, you can actually do a pretty good job of doing few-shot learning, but it has some drawbacks as well. And then finally, we have this in-context adaptation. And basically, the idea of this is that you throw all of your kind of experience into some kind of context history, and you also have a kind of hidden vector that gets kind of updated over time, like recursive neural networks. The challenge with this is that it actually requires extensive simulation training. So the secret of this kind of video is that they've done thousands or millions of trials of simulated robots, all with perturbations given to them. And so they're able to adapt kind of their current model online to kind of fit one of those kind of previous instantiations of a simulated robot. But they do this implicitly. It's not an explicit thing like a parameter estimation. So with all of these, there's I got very interested in kind of understanding all these different techniques because we had a project from NASA. This was a kind of proposed Europa project. It actually got canned because of some political reasons, but they wanted to send a lander to Europa to do some drilling for ice. And from the Curiosity rover, one of the problems with drilling is that you have a very hard time actually figuring out exactly which parameters of the drilling forces and speeds and so on would end up giving you a useful sample. And so when they sent this out to Mars, they ended up failing with the kind of parameter settings that they tuned on Earth. And they had to actually use kind of human revisions and teleoperation and so on, which was okay for Mars because of the short round trip times. And they ended up getting the sample, but after human intervention. With Europa, it's so far that it's very difficult to be able to do that sort of thing. And also you're shaded by Jupiter as well for large parts of the kind of operation of this lander. So the hope was to automatically figure out like a human scientist would, how to adjust your parameters to be able to then get a good sample. And so the goal is to do earthbound training so that we are confident in the deployment in a completely unknown environment that could be completely out of distribution. And we trained a model based off of Gaussian processes to predict scooping volumes. And we found that this transferred immediately to a JPL testbed that we hadn't seen before. So this is kind of nice. I won't go into all the details about this, but let me just give you kind of a sense of why this is tricky. So suppose that offline you've seen some rocks and you've seen some sand. That's your pre-training set. Your sand is very easy to scoop, right? And it looks kind of tan. The rocks, much harder to scoop. You kind of get jammed in them and you can't really pick up too many of them. Now, let's say online, you get a very out of distribution kind of case. You see on the right, there's a big cardboard sheet. You can't scoop a cardboard sheet, 0 volume of sample. So your base model is going to predict high volumes if it's been pre-trained with any kind of quality. But with the online data that you get, the failures, you can tune to that kind of set of failures and then learn to predict somewhere else. So our method, in contrast to a non-adaptive approach that just keeps on trying to scoop this kind of cardboard sheet, instead our method scoops a couple of times on the cardboard sheet, learns that the visual relationship between this kind of tan-looking thing and the scooping volume is actually much lower than expected. And so then it adjusts to scoop on the right in just 3 samples. And we've done all sorts of very unusual kinds of testing, out of distribution testing terrains, pasta, packing peanuts, Lego pieces, and also this cardboard sheet. And the real trick here is that we were using, that we have to train this Gaussian process model in such a way that it's well calibrated to account for this out of distribution shift. So if you know anything about Gaussian processes, you'll know that there's a kernel function. And this kernel function can be actually well, you can represent these as a neural network. And the challenge is that you have to calibrate these in a kind of to account for this out of distribution shift. We can train these in a kind of standard way using negative log likelihood. And with these kinds of deep methods, we use this kind of feature transform G, then pass that through a more standard kind of kernel, like a Gaussian kernel. And this works reasonably well, but it assumes that the mean is 0. And we want to actually get some information out of pre-training. So instead we use this technique, deep kernel and mean training. We're going to be learning the mean estimate, which is this first network here, M, and then we have a GP residual. So this is a popular approach, but one of the problems with out of distribution generalization and calibration of this kernel is that if our mean has high capacity, then our residuals are going to be close to 0. And so this GP has basically nothing to go on. It doesn't really know how to deal with something that's a non-zero residual. So it's very, very tricky to tune the capacity and the regularization strategy for these learning problems. So our strategy is to do something a little bit akin to cross-validation. Our technique was called CODEGA, or controlled deployment gaps. Basically, we meta-train so that the residuals are high. We split our pre-training, or kind of simulated pre-training and adaptation steps into different splits that are as far apart as possible. So we're basically forcing the mean to make mistakes on this kind of adaptation set. And then we're calibrating the kernel on the adapted residuals. And this works pretty well. So compared to other methods, you can see in the upper right, our method, which is shown on the left there, has much fewer number of attempts to get a certain type of scooping volumes on these out of distribution terrains compared to some of these other methods, including some adaptive methods, some RL-based ones, and also a kind of non-learning based one called volume maximization. So this was quite interesting, and so this really got me started to think about adaptation in a deeper way. But one of the problems with this approach is that it's only looking at a single number. It's adapting a single prediction, which is the reward. Now, what about learning dynamics models? That kind of got me thinking of scaling this up. We need to do something else to scale this up. So recently, we with Yunju Lee at Columbia, we worked on this graph neural network based dynamics model that adapts to the observations online. It's called Adaptograph, and it's a material conditioned graph neural dynamics model. So Yunju Lee he's had a lot of work on these graph neural network models. Basically, we have a graph neural network that predicts how each of these particles is going to move. And we can roll out that model to get a kind of long horizon prediction. Now, previously, these were trained to a specific type of object with a specific set of material properties. And in this paper, we trained on lots of different types of materials and also lots of different object types as well as their material properties. So during training, we used a simulation and randomized a bunch of different material parameters, built this physical property condition graph neural network, and then when we observe online data, we can take these particle positions and optimize the fit of the model to the online data. And so this is the online physical property estimation. This works a lot faster than fine tuning. We can take just a few handful of examples and get better fits to these material parameters using this approach. It's just like explicit optimization. And you can see that if you just take, for example, the average model for this box pushing case, you end up getting just bad dynamics predictions and the planner doesn't know what to do with it. Whereas with our technique, it quickly converges by adapting that material parameter. Same thing with this rope straightening example. It's kind of struggling because it doesn't have the stiffness of the rope properly estimated in its dynamics model. And then in our method, which should play here soon. There it is. It goes. It figures out the material parameters and ends up straightening the rope. And you can see that this works for all sorts of other types of approaches because, other types of objects, because graph neural networks are quite a flexible kind of representation that allows you to represent all sorts of different objects with just a network of particles. So both qualitatively and quantitatively, we have better results using this approach. Yes, please.
Are you modeling occlusions in the graph or aliasing across the nodes with?
No, so there's no modeling of occlusions. So if you did have significant occlusions, you'd have to do kind of a better job of data association. That's actually one of the biggest challenges with getting this type of thing to work. When there are occlusions, you can't exactly know from an observation which of the particles it should be associated with. Yeah.
Thanks.
Yeah, you're welcome. Okay, so closing out this section, so we are able to use various forms of mechanisms to do adaptation, right? There's a whole host of them, and none of them are perfect. I'll say that just right away. Few-shot learning is not a solved problem. If you want to do something theoretical, give us better few-shot learning algorithms. I'd love to see some advances in this case. GNNs are very flexible base representations, but there's the data association problem, just as you mentioned. Also, I will say that training is not particularly stable, and we had to do a lot of work to get the training to work well for all of these cases. And the problem that I'm going to switch to now is actually scaling up in terms of heterogeneous deformable worlds. So if we have heterogeneity, and our unknowns are about all of the different types of material and physics properties of everything in the world, this unknown vector theta is massive. It could correspond to every single material property of everything that it could potentially work with. So that's really the challenge we're going to be looking at next. Even in the pre-training sets, we can't estimate this value. And it's also really, really hard to train in sim. Right? If we just randomize the material parameters of a bunch of deformable objects, well, the sim is probably going to blow up. Right? So let's think about how we can treat the world as a bunch of stuff. We do need to learn a little bit more about deformable object representations because these stuff models have to have some kind of aspects of deformation in them. So there are analytical methods to represent these kinds of deformable objects and deformable worlds, spring mass systems, finite element methods, material point methods, etc. And there's also data-driven methods that try to model deformations purely as some kind of neural networks, either image-based or neural deformation fields and also graph neural networks. So you'll see kind of instances of these on these kind of images here. Analytical methods have some advantages. They're physically grounded. They have great spatial temporal predictions. You can generalize between object geometries pretty much for free, but they do require you to choose constitutive equations carefully. Going from perception to the simulation mesh is very challenging, and identification is really a key challenge. Whereas with data-driven methods, you can discover the physics from data. They're very, very flexible. You can basically directly or near directly take perception inputs into these models, but they have low precision, they have long-term instability, they don't generalize super well, and they can also smooth and average.
Hey,
So in the previous,
question,
yes.
do you have to go to chemistry
Do we have to go to chemistry?
there to really
Yes, good question. Do we need to actually understand the physics, right?
interact
R-
with each other?
Right. So if you take actual physics into account, that's more of like the first class, right? Oh, even chemistry. I don't know. So the thing that we're seeing with data-driven approaches is that you don't need to understand absolutely everything about the physical properties, right?
Introduction chemistry to learn, because I never had that.
Yeah, great. So our previous approach was trying to address a couple of these issues with these data-driven methods, but I want to kind of focus on the kind of other method as well. So I will also say that several researchers at Penn came up with this PIXI method just this year. Very cool work trying to address how to go from perception to simulation meshes, including the estimating the material parameters. Very cool stuff. I'd love to talk to you guys later about this. But the techniques that I'll be talking about now in this section are going to address these two problems simultaneously. So both perception to simulation meshes, but also the identification problem. So online adaptation is really the key here. So how do we actually feel these kinds of models and observe what's happening and build these models from scratch? And I'm really inspired by some previous work on touch-based modeling of worlds. So there's work on palpation, for example, that tries to identify which kinds of objects underneath the kind of soft tissue are stiff. That's the obvious application here, is doing something like palpation for cancers. But there's also work on kind of blind robot reaching, some from Georgia Tech, others from Michigan, where you're using touch sensors to be able to figure out just what's around you in some kind of cluttered environment. And it's using that kind of inspiration from prior research. So one of the techniques that we've worked with is called volumetric stiffness field. Hopefully that'll play. No, it does not play. Okay, now it's playing. All right. So the idea here was that we're going to just throw a bunch of particles out into the world to represent our object. And it can be tens of thousands of these. And we're going to have just very, very simple models of dynamics for each of these particles. Each of them is just elastically attached to its reference point with a spring, just a hooking spring. And we're using force and torque estimation from any number of sensors, along with a very, very simple simulation model, to build a very simplistic model for each of the individual particles. So we have this extended Kalman filter framework running for each individual particle individually. Now, this is a super simplistic method of what's actually going on. It's very approximate, but it's very easily parallelizable, and we can run this online in about 10 to 15 hertz for tens of thousands of particles. So we get these joint torques or force torque sensor data, or as I'll show in just a bit, dense tactile sensor data. And we're able to then incorporate this into an estimation and then build up these stiffness distributions that can be used to predict future sensor interactions. Okay, this seems to be a bit buggy here. Sorry about that. And PowerPoint might just be crashing. Well, this is time for me to answer your question, Mike.
What's the connectivity like between the particles? Is it
Nothing. So there's no connectivity.
You have springs, right? So they must attach to something else.
They're attached to the reference points. It makes no sense for very large scale deformations, but it's like the only thing that would run for something like a plant, right? You can't estimate the connectivity of a plant. It's very, very challenging to do this accurately. I have some colleagues that are working on this AI Farms AI Institute that are trying to do that. They're trying to actually build accurate 3D models of the plants, but it's really tough. They're not working accurately. So the point is to like throw away all of our models entirely and just kind of, well, all of our kind of detailed correct models and just do something approximate, but estimate in parallel across the entire volume quickly. And this outperforms other kinds of learning-based methods like learning from joint positions and so on. And we can start building these models and using them. Oh, yeah. Yes.
If you took that robot arm and you touched a different part of the plant, would it just fail at that point?
Yes, it completely fails at that point, and I'll talk about how to address that in just a second. So, but you can complete. Okay, this was working just a second ago, but now Zoom is somehow angry at me. Okay, let's go back. Okay, it's even worse. What is going on here? Okay, somehow that worked. All right, so you can use this for blind motion planning. So if you don't even have a vision sensor, you can just kind of go and feel things, and then you can create these kinds of estimates of resistance, and then go around them. And with multiple approaches, multiple attempts, you can get around these kinds of obstacles. This is good for plants because, well, there's no real definition of what is an obstacle with a plant. Right, you can go ahead and it's very easy to just touch the leaves of the plant. There's no damage that can occur to your robot or the plant if you do that. But for running into branches, that can be a big challenge. So you have this kind of problem of like, how conservative do I want to be if I'm trying to get around this plant or reach into the plant to go and, let's say, do some picking or to, let's say, do some inspection of the stems of these branches. So another thing we've done is work with these high resolution tactile sensors. So this Ponyo sensor over here gives you this mesh of forces that can come out of it. And by touching the object, you can get a sense of how it resists in different locations. And one of the challenges of using the kind of particle-based approach I just mentioned is that there is a mismatch of accuracy or resolution between the particles and this high-resolution sensor. So we came up with this technique called neural VSF. It's a nerf-like representation of the stiffness field. And we were able to learn this through touch. And the idea is that we touch the object several times with this kind of sensor. And then as we get more information, we can then run an optimization of this neural stiffness field and then get this representation of the stiffness of the object. We can do some cool things with this. For example, blind localization. We can take this kind of stuffed animal toy, put it underneath some kind of cushion, and just use the touch information and figure out where it is. It turns out to be more accurate than using some sort of fitting with like a reference model of like a 3D object using something like ICP. But so we were actually matching the stiffnesses that we feel in the online data with the predefined model. Now, getting back to your question, Michael. So, I mean, touch is a very impoverished form of sensing, right? You touch one object and it doesn't give you any information about anything else that you haven't touched, right? So we want to be able to make use of cross-modality correlations, vision and touch coming together, right? So the way that we do that is through a technique Bayesian meta-learning. So we're trying to meta-learn the correlations between these different modalities. So we have some kind of offline data set where we've touched these objects quite a bit, and we've also captured visual information about these objects. And we learn this meta prior, which tells us something about how the vision and the vision, position, and the stiffness are all correlated together, right? And then we can use that to instantiate it for a new object. Why it's a structured meta prior, there's a lot of like technical details here that I'm not going to go too much into, but basically we're trying to learn a kind of latent vector that is estimated that kind of governs not just the material properties of each individual point, but also commonalities between the points. And that's this vector phi here. We can create different types of structures between latent vectors and the kind of correlation structures that we are assuming. I'm not going to go into too much detail about how this works, but basically what we're thinking of is the kind of decomposition of the dense stiffness covariance between all the different particles of your model in our VSF approach. It's like a diagonal covariance. There's no correlation between information from one point to the other. If you're thinking about some kind of homogeneous component, it introduces, so let's say that if I touch an object at one point and I assume that the rest of the object behaves the same, then that information I get from touching that one point should propagate itself through to all the other points. And so this idea of this kind of sparse decomposition of the stiffness covariance is that we basically think of a kind of constant column in this, this basically like a symmetric decomposition of this matrix. We can also think about segments, so that if you have an object with a bunch of parts, then each of those parts having similar kinds of covariance, you can basically create that kind of correlation structure as well in this kind of decomposition. And with this, once we learn this kind of meta prior, basically these features here, F, those are all visual features and position features. And those can tell you a bit about how those features are correlated with the ultimate stiffness. And so what's great about this is that we can zero shot take a look at an object and predict its stiffness. And we can update that as we go as well by touching it. So with zero shot, we're able to predict with similar accuracy to 10 to 15 touches as in the previous vanilla BSF. So that's pretty cool. And so we're trying to build these databases of objects so that we can kind of generalize this information to objects within the same class. We're still limited to certain classes of objects. So we've built a database for plants. We've built one for shoes. We don't quite have one for like general objects across the world yet, but that could be interesting for future work. So for this volumetric stiffness field, we have an open source project, OpenVSF. You can use basically all the techniques I just mentioned, and it's pretty robust and used in a bunch of other projects as well at this point. Some limitations of this approach is that only elastic deformation is supported, and we only acquire vision once. We're not watching how we're touching the object, and we'd like to be able to do that, do something with that vision information too. And also, we're manually prescribing these latent spaces of whether it's homogeneous or heterogeneous, and whether there are part segmentations. We'd like to do something with that more automatically. Now, so to address some of these problems, like so, if I touch a part of an object and the whole object moves, right? I need to be able to capture that kind of correlation. I want to be able to learn that automatically. And so I was inspired by some of the work in using map belief dynamics for exploration. So if you haven't seen this kind of field of object goal navigation, it's pretty interesting. You can take partial maps that you see occupancy grids of worlds, and you can predict what's behind the kind of unobserved regions of these worlds, and you can update them as you go with new sensor information. People have also been looking at this problem of mechanical search, where you can move things around to try to look for a certain object. You can use some neural representations there. But the question I was thinking is, can we use map beliefs to represent these worlds of stuff? So rather than thinking about this kind of Lagrangian particle-based representation, can we think about an Eulerian representation and propagate these maps forward to represent our kind of stuff models? And this year, we showed how we could do this for basically searching in a cluttered scene and mapping out a cluttered scene. This technique, calibrated neural accelerated belief updates, basically take map beliefs and update them over time as we either change viewpoints and observe different parts of the scene, or if we manipulate parts of the scene through pushing. These are metric-semantic maps, so they also include object identity information. And we learn the propagation through viewpoint changes and these pushing manipulations. And we use them in a POM-BP planner. These are, by the way, supposed to be playing at the same time. I guess can I start them at the same time? Okay, they're almost coordinated, but you can see how this map here, it's got these different labels for the different objects that are in the scene, and it also has this kind of grayscale indicating the confidence of the occupancies in the scene. So with this technique, the way that this works is that we have these basically 2.5D kind of height map representations. They have the segmentation and the occupancy map and also the height predictions. We're learning the updates of those through viewpoint changes, where we basically get a RGBD plus segmentation from a new viewpoint. And we can also learn the dynamics through pushing, through using a simulator of these cluttered scenes. And so we can push and change viewpoints. And we throw this into a POM-BP planner, and we can actually adjust whatever kind of objective function you want, or the reward function for changing these maps. We have an objective function that's information gain. So we're trying to optimize information gain and basically learn the whole map in this kind of evaluation here. And we can show that with this kind of objective, you can improve performance using our technique. So these are plots of a bunch of different things. I'm not going to go into too many details about them, but there's a few boosts that we get here. Our technique is that orange line. We get this first this boost from map completion. So these neural map belief update methods are actually giving us something here, actually quite a bit. The information gain metric that we're using in the PalmDP planner also gives us a little boost as well, but the manipulation part is this little boost over here. So you can see that it doesn't really help with occupancy, but it helps a lot with semantics. So because like if you just push everything into the back, you know that everything's basically occupied. So you don't get too much benefit from manipulation there. But if you want to actually get the identity of objects, you can see that it helps a lot to be able to manipulate because you need to pull things apart so you can get the identity of these different things in the back. We also zero-shot transferred to the real world with the YCB object set. If you just do random actions, then you don't get a lot of successful identifications of objects. If we don't use manipulation, we get about something like 65% or so of successful identifications. And with our technique, it was about 80% of successful identifications of a target object that was not seen from the first. It's not obviously seen. It's somewhere in the back. We actually created some pretty tough scenarios where a bunch of large objects were blocking the back. The kind of gap between this kind of green, the light green, and the dark green is that basically there was a mistake in segment anything model, and the identity was not identified correctly. But it's as perception gets better, hopefully this will also get better. Okay, so some takeaways here is that we're getting some benefits from treating the world as very dense kinds of representations of stuff. The estimation is key. We want to have few-shot estimation, even zero-shot estimation for the kind of material parameters of these particles. We're making progress in several dimensions, but it's really hard to actually unify all these desired criteria. So here's our most recent paper submission on this was using graph neural dynamics models and trying to basically improve its ability to do mapping on larger scale. So we're kind of hitting little boxes here, but I don't have a great solution for basically getting all of these at once. There's some challenges here. We need to be able to represent very rich environments, but we also need to have estimation be fast. We don't want to have to rely on high fidelity simulators as well. We want to learn from real data, hopefully. Generalizing across lots of object classes, basically just taking a single image and figuring out its material properties, but also being able to adapt those over time is a big challenge still. And also just in terms of acting, we don't know exactly how persistent these representations need to be over time. Can they just be short-term representations that you throw away after you've interacted with the object, or do you have to memorize exactly what you've done many, many hours ago? But we're still far away from doing what this little chihuahua can do. So that's where I'll kind of stop on the technical aspects of things. I'm going to switch over to the last section very briefly about hot takes. So students come up to me and they say, rather than, "Oh, I really like the paper that you wrote," they'll say, "I really like the hot takes on your website." So I'm known to be a little bit kind of pessimistic about things, maybe a little grumpy. And I think we're in kind of a worrying point in time, I'll say. One thing I'd like to say is that publishing has changed a lot in robotics. This has happened with computer vision, but publishing has become very imitative. Right? People are not trying to necessarily innovate with every new paper, but they're trying to imitate. Just as an example of this, I'm going to switch over to this website here. So here you can see that I have this ICRA paper title generator. I came up with this when I saw in the senior program committee meeting all the names of these ICRA papers, and I was like, wow, they're all basically just Cartesian products of a technique, a kind of application area, and also a task. So this is not ChatGPT. This is just random number generators, and you can see if I just repeatedly refresh, I'll just get a bunch of new paper titles. They all look like pretty reasonable, right? And so, okay, I went drinking with a bunch of people, and this is my drinking game. I would have like one synthesized paper title, two real paper titles, and your goal was to guess the fake one, right? Shockingly low results. My student actually did a kind of test, a systematic test. He went to 100 people and did this. So, right, the chance is 1 out of 3, right? Guess how many people actually got the right one correct out of those 100? 41. Right? 41 out of 100, just a little bit better than chance. And I think that's very scary, right? Like this is really not good for the field, right? We're having huge amounts of papers published, all of them sets of problems rather than classes of problems, and not really building knowledge upon previous papers very effectively. Our review process is also degraded, right? Because we have a huge volume of people coming into the field, reviewers are more junior and just have to go with ChatGPT. And so rather than merit being judged on the quality of your ideas, it's basically the amount of viral marketing that you give to your paper. Right? These are how ideas are being shared. We're de-emphasizing understanding. We're emphasizing just more and more activity. Mentorship is getting worse. Junior faculty are feeling the pressure. It's not a really great situation. The AI genie is out of the bottle. Like the AI generation of papers is going to increase, the AI reviewing of papers is going to increase, but it's not just about papers, right? It's also about AI across the world. This is a really unique time in space in that there's so much into AI as the way to solve your problems. Problems with people who have money is that they want to get rid of jobs, right? They want to save money for their companies, and they want to even richer billionaires. We have a lot of hype. These companies don't have any product that actually adds any value to the world, but they're valued at tens of billions of dollars. Insincerity is being rewarded, right? The more that you can lie, the more bald-faced your lies, the more billions you get. This is all huge societal problems: wealth inequality, right? Dehumanization, difficulties in learning, right? Students are using ChatGPT even at age 8, right? As soon as they can type, they can use ChatGPT. And so what's the future for academia in this kind of where AI is taking over? With all the geo as well attached to AI, right? We're seeing not just, Silicon Valley billionaires, but we see why to invest in infrastructure and energy infrastructure. Who knows what's going to happen when robotics takes off, right? It's going to be robot armies controlled by AI, controlled by a few billionaires. And so we have a very uncertain future with economic turmoil just around the horizon. And what are we to do, right? Do we just go along and hide? Do we just kind of try to keep under the radar and just keep doing our stuff? Or do we, for example, try to get as many resources as we can, protect our families, and run, right? These are the choices that we have to make. Samsung Research is hiring. So I'm building a R&D team, doing advanced R&D in Silicon Valley. We do papers and patents and partnerships. We fund universities as well as startups. We've got generous compensation as well, Silicon Valley kinds of competitive pay and benefits. We're in the heart of Silicon Valley, just next door to Intrinsic and right down the street Google, NVIDIA, and so on. And we're hiring at all different levels, junior and senior interns, as well as consultants. So all of you professors in the audience here. So, okay, but getting back to what I wanted to kind of get to, so, there's so much investment being done, academia is going to have to change its role. I can see this, like the amount of volume and scale that industry can do is just completely outshining what academia can. But if I were to, let's say, be fully staying in academia, I would definitely be thinking about cognition. So there's a long view of cognition here, and industry is not going to focus on it, and we're not doing a great job of it in academia yet, but I think we could. Okay, that's supposed to go up to a little bit at a time, but so if we were to think about integrative cognition, thinking about the problem of how robots can think and how humans can think, right? Humans do all sorts of things. It's not just system 1, system 2. It's not just reflex and then some kind of VLM on top of it. we judge, we have attention, we have memory, we form symbols, we have some kind of spatial understandings, physics understanding, emotion, etc. These are all known to exist. And if we can somehow understand those better than the psychologists and the neuroscientists who just kind of focus on their one area, we're one of the only places where we build kind of full systems that do cognition. And so if we were to like give back to like a scientific contribution to society, I think one thing that robotics could really get together and help with is to shed some light on cognition and how it actually works and what are the key essential ingredients of cognition. I don't think it's just data. Humans are not just data processing machines. It's not just data at scale. But we have to stop thinking about just getting things to work. We need to stop thinking about demo culture. We actually start having to work very closely together. And I'll just close with this slide. You know, if astronomy, physics, and computing can do it, why can't robotics? Let's all get together, work on big problems. Let's try to solve these kinds of huge problems of cognition. And with that, I'd like to thank the students that worked on this, and you can take a look at some of these websites. Thank you so much.
Oh yeah, thank you for the awesome talk. I have a question that the problem of the patient and like 3D deformation representation is interesting, but at the same time, there are some opinion that video model can learn some that kind of adaptation or like deformable 3D representation by internally, kind of like that. So
That's right.
I want to hear your opinion about the video model and the world model.
Yeah. So sure, I think video models and world models are. I hate the term world models because I don't think they're actually modeling the world. I think we're trying to actually model the world. But in any case, that aside, the kind of context, I guess, and the drift, I guess, is the issue of these kinds of forward prediction models. You can't necessarily keep the kind of memory of an object, in context for all that long. And whether or not just throwing more data at the problem will actually solve this kind of persistence problem or not, I don't know. But at least for the short term, being able to actually reason and it will work with the memories. Like we can take a VSF model and you can manipulate it. You can throw some kind of modifications on it if you wanted to. Right. And so you have something that you can manipulate versus this completely unexplainable thing. So I think there's some advantages about explicit models versus implicit models that I think as an engineer, I really like to be able to get my hands dirty and actually touch something with that model rather than just relying on a black box. Yeah.
Thank you.
Thank you for such a nice talk. I suppose the world is too big to represent as a volume of particles and springs and stuff, right?
Sorry.
The world is too big, it's too diverse. So at some point of time, I need to move away from dense representations of the environment.
Yes.
And what do they look like?
Yes, so that's kind of this last point here, right? So the permanence and the resolution of these representations is something that we need to think about. So the long-term memory, of course, we as humans, we don't remember absolutely everything about everything that we've ever seen, but we'll remember some kind of key points. And so this kind of abstraction of kind of dense data into sparser representations is something that we can look into. It's something I'm very excited about looking into, actually. We can basically cluster certain like parts of objects into kind of regions and kind of remember something about them. I think the challenge then is to once you go back and kind of close the loop, right? This kind of loop closure problem, taking a coarse piece of information and then now you want to reestablish some kind of dense representation. That's going to be a very interesting kind of problem. And that's kind of, I think, the new kind of area of estimation that I think we should start to look into. Multi-resolution kind of dense estimation. Yeah.
I really like the particle-based representation that you're pushing, and I think the modeling of dynamics is really impressive. But in terms of specifying tasks, like cost functions for your controller, how can we get beyond things like just chamfer distance, like where you just maybe care about transporting particles? But let's say I have a task like I want to tie a knot. Like, what do you think are the challenges to scale to more expressive tasks?
Yeah, that's a really good question. I think my approach as a kind of old school person would be to think about this as a kind of modular AI kind of approach where you would take some kind of, let's say, if you have a very complex kind of hard to specify, not really mathematically well-defined objective, throw some kind of learning on top of that and try to learn the kind of predictor for some, let's say, reward or goal for that not tying case. For some cases, like if you're trying to reach into a plant to go pick something, I mean, it's the targets are very easy. It's just kind of a 3D position in space. But those more complex tests, I think some kind of learning is going to have to go into this. Yeah. There was a question here.
Hello. Thank you for your talk, by the way. For the representation of spring particles, is there an idea to like add directional stiffness to those, or kind of what are the thoughts on like the future of that type of
Yes,
research?
yes. So that was actually very early on. We were thinking of doing anisotropic stiffness matrices. So basically, you have a 3x3 matrix you're estimating rather than just a single number. It's kind of partially supported in Open. I don't think it's actually fully integrated in OpenVSF. There's kind of like plans for that. We found that it's at least for the objects that we're looking at, it's okay to just use a kind of single number. But you can think like for branches, a branch is springy in one way, but if you try to press it in the other way, it's very stiff. So yeah, I think that should be on the roadmap, but we just haven't had time to look into that. We're doing things like, estimating these VSFs with the objects kind of moving around and doing all sorts of other things, packing those objects. So it's on the roadmap, but if I had more students, I could actually start to address those. Yeah, thanks.
Oh, Antonio, why do you do this to me?
Exercise plan.
Stairs.
Okay, it seems to work. Very cool, very interesting. I have one question about the hot takes. And the question is, why are you so pessimistic? Feels like things are going pretty well. Robotics is going at a pace that was not going before. There are so many interesting questions. And sure, I see the things, the negative things that you noted, that's for sure. But that's been there in research all the time. There are going to be few people that can think differently and they are going to make a difference. The people that imitate, they're going to have a very short half-life, so time is going to forget them. But I think it's a very exciting time to work on. I see the geopolitical and social problems, but I mean, this is there for every technology, like not only robotics.
Yeah, yeah. Well, so the one of the reasons why I'm pessimistic is that it's hard to, well, first of all, just like, I mean, look at all the stuff that's going on around us. There's just how we get motivated to work on the things that we work on. I think it's just an important, very also personal kind of question for everyone. And what I'm seeing is that the kind of motivations of people, just more and more that I'm seeing, especially like the younger people kind of getting into the game, it's not so much about really trying to deliver some sort of understanding, but rather than it's trying to kind of parasitically kind of like jump on the bandwagon and like ride the hype train and try to get some kind of jobs at the end of this, or get investments for their startups. It's not so much that you're trying to deliver some kind of academic understanding that academia is typically best at. So I think I'm concerned about that. But I think I'm also concerned about our ability to deliver good ideas and being able to discriminate good ideas from bad ones. So academia is also a place in which you are supposed to kind of hone that ability to discriminate, rather than like, so in a world of cheap generation, discrimination is the thing that has value. And as a teacher, as a researcher, I was having a harder and harder time kind of shaping the kind of discriminative power of my students, as well as the people that I talk to. So, as more people get into your field that kind of are inexperienced, right? We have this kind of huge influx of kind of like people who are new to robotics. Those people in a couple of years, they're going to be the professors of robotics, and they're going to have a certain kind of mentality as well. And this kind of idea that you should just generate a ton of papers and just keep on trying new things. And it doesn't matter if you've actually just taught the world anything with your paper. It's not healthy. I see junior faculty that I even work with who just, I'd say, hey, this paper isn't ready. There's no solid idea here. You just tried a bunch of stuff and something kind of stuck, but it gave you like a 5% benefit in segmentation accuracies or whatever. And they're like, just publish it, just submit it. It's too much pressure for junior people. It's too much kind of emphasis on just generating activity and not enough emphasis on cultivating thought, right? And in a future where AI is extremely powerful, your value is going to be in doing better, right? To actually have very solid ideas and understanding that can correct for the mistakes of AI. I mean, and AI papers, we're going to be flooded with AI papers, and we probably already are starting to see that.
And maybe if I can follow up like real quick on the one of the first slides, you said we need cognitive representation, and then you showed like 10 desiderata. And I was wondering if you think this is going to be just one representation that makes them all, or something a bit more specific.
Well, I'd love for something more general. I'd love for, represent anything, something like that. Right now we have just some special purpose models for special applications, and it's not great to have that. Just in terms of like fragmentation of the community and wanting to build kinds of activities and behaviors and applications around these kinds of representations, the more general, the better. This is something that computer vision does very well, is that they define a certain problem class that works for a lot of different things, and then people can focus on that kind of problem class. And if we were to also do the kind of same thing with these kinds of representations and define what it is that we want from them, and then start to iterate towards that, get better and better at it, then I think that would be a much better kind of state of operating than just the way that things currently are. Thank you. Yeah, great questions.